So folks, in our last video, we looked at the definition of divergence, and our very last vector operation that we're going to learn in this course is the curl. Now, we've already studied the 2D curl back when we did Green's theorem, but that's a little bit misleading because the 2D curl was a number, but the actual curl that we're going to be defining for vector fields in R3 is going to be itself a new vector field, or if we're talking about a the curl at a point, the curl at a point will be a vector. So if we take a vector field f, and here I've set it to be in R3, so I need to change this to be in R3, and in fact the curl is only defined, the true 3D curl is only defined for vectors fields in R3. And the curl of f is, first of all, we're going to denote it del cross f. Okay? And again, we've introduced this del operator, so we'd read this as del cross f is one way to say it. The other way to say it is to say the curl of the vector field f. So when you see this cross product, think the curl of the vector field f. And the nabla notation, or this del notation, gives us a mnemonic for remembering how to compute the curl. So you know how to compute a cross product. We've always put I, j, and k, and then we put the two vectors inside of this, and we compute this 3 by 3 determinant. Well, if this is our vector field, we know that the last row, give yourself room, we know the last row will be f, g, and h. The question is what goes here, and that's where we introduce this del notation as a sort of way of, a mnemonic way of remembering the formula. So we'll write partial x, partial y, partial z. Remember that del operator is simply this vector-like thing that has the corresponding partials for each of their component functions. And now we know how to compute a cross product, so let's go ahead and do so. So for our expansion by minors, we'll have this product, and again, this is where this is just a gimmicky mnemonic device, but what does it mean to take this and multiply it by h? That doesn't make any sense, but we're going to take the partial derivative of h. So in fact, we'll just write it this way. We'll write let's go ahead and write partial y, partial z, g, and h, I hat, minus, and then we'll expand by this one. We'll get partial x, f, partial z, h, j hat, and then plus partial x, f, and partial y, g, k hat. So what I was about to say just a moment ago is we can't actually multiply these together. One is an operator, one is a function. We'd have no understanding what that multiplication would mean. That's why this is just a gimmick. But instead, we think of taking the partial derivative of h with respect to y. So we'll write partial h, partial y, minus partial g, partial z, I hat. Then there's a minus in the formula, and we'll have partial h, partial x, minus partial f, partial z, j hat. And then finally we get partial, and we'd have partial x, partial g, minus partial f, partial y, k hat for our third component. So here is our cross product operation. So you could just memorize this formula here, but nobody actually memorizes that formula. It's too hard. So instead we build it every single time we need it using this del operator notation. So we'll take del cross f, and you just go ahead and actually compute that cross product. The thing that I want to point out is when we introduced what we called the 2D curl, we were being somewhat misleading in that the only thing we ever looked at in the 2D curl was this scalar in front of the k hat component, and that was because we imagined our vector field in R2 as living inside of R3, and so we just needed that number when we were looking at what we called the 2D curl. So this was the number that corresponded to the 2D curl in section 17.4. But this whole thing will be our 3D curl, and you really should start shifting gears here to thinking about the curl as always being a vector. One quick note, when the curl of the vector field is 0, oops, this is an error, folks. This should be the 0 vector. When the curl of a vector field is 0, then we say that the vector field is irrotational. Okay. So when the curl is always 0, we say it's irrotational. When the divergence is 0, we say that it's source-free or incompressible. Okay, so let's actually practice this. Let's go ahead and compute the curl of the vector field that we were just looking at. Or I guess it's slightly different, but a similar vector field. So we want to compute this curl, so we want to compute del cross F. And I really do think that this mnemonic notation is helpful because it gives us our way of unpacking the formula for computing the curl. So we'll do I, J, K, partial, partial X, partial, partial Y, partial, partial Z, and then we'll put in our component function. So there's our X squared Y, our X plus Z, and our Y minus Z squared plus 3X. And we'll go ahead and compute this cross product. So I'm not going to write the minor submatrices. I'll just go ahead and do the computation. So for our I hat component, we're going to take the partial derivative of this component function with respect to y, and if we do so, we get 1 minus, and then also for our I hat component, we're going to take the partial derivative of this component function with respect to z, so we get minus 1 I hat. Minus from the formula, then we're going to expand along this row and column. So for this minor here, we'd have partial, partial x of this function right here, which is 3, minus partial, partial, the partial derivative of this function with respect to z. So that's 0, j hat. And then for our third component, we have partial x of this component function, so that's plus 1, minus this partial derivative, and the partial derivative of this component function with respect to y is x squared, so minus x squared. So if we clean all this up, we get 0 I hat minus 3j hat plus 1 minus x squared k hat. And I forgot my k hat right there. So this is our curl. Notice that the curl itself is a new vector field. We've got 3 new component functions. This is constant, but this is a function here of the 3 variables x, y, and z. And so we've got this new vector field. So the curl itself is a new vector field. And now we're asked to compute the curl at a point. So if we go to compute the curl, and again I'm practicing just using various forms of the notation. So the curl of the vector field at that point will just be 0 I hat minus 3j hat plus 1 minus 1 squared k hat, which comes out to be the vector, we'll go ahead and write it in this bracket notation, 0, negative 3, 0, which is our computation for the curl at that point. Now, the question that you should have is, what on earth does this mean? And that's something that we're going to explore in more detail in class, because it's just a little bit hard to talk about this curl. I feel like divergence is a little bit more friendly to go ahead and access right off the bat, but we'll talk about this curl more in class. Okay, so at this point we've introduced this del operator notation, and we've got a lot of different actors at play now, and it can seem a little bit messy. So I just want to remind you that this is a scalar valued function. And I'll ask you this a couple more times in this document. This is a scalar function, so we take del dot f, and it at each point the sinkiness or sourciness, I don't even know if those are words, at that point. Okay. So this then is a number, and it corresponds to whether the vector field behaves like a sink or a source at that point. With the magnitude of that number being how much of a source it is or how much of a sink it is. Okay. So we've got del dot f. This is our divergence Okay? And then we've got del cross F. This is our curl. And the curl is itself a new vector field. Okay? And we haven't really given an interpretation of this yet. So we'll just leave that open. Okay? We haven't given an interpretation of that yet. Now here, we're looking at the curl at a point. So this is a what? This is a vector. So how do we, so the curl of a vector field is a new vector field. So if we evaluate the curl at a point, this will give us a vector corresponding to what? Well, we haven't said. Okay. So I'm going to get into more detail in this in class, but let's go ahead and look at a couple of GIFs that show us the curls of some simplistic vector fields. So if you click on that first GIF, this is what pops up. And this is how we imagine the 2D curl back at the beginning of Green's theorem, where we said, okay, we could imagine sitting inside this 2D vector field. We could imagine fixing these pinwheels at various points and then asking the question, to what degree do the pinwheels rotate and in what direction? And if they rotated, as this one does, in a counterclockwise direction, that corresponded to a positive curl. At this point, we're rotating in a clockwise direction, so that corresponds to a negative curl. And then the magnitude of the number corresponded to how quickly we were rotating. So here we have a very small but positive curl. Here we have a very large negative curl. So this is how we looked at the curl previously. But remember, going forward, the curl is not just it's not a number, it's in fact a vector. So if we go ahead and actually compute the curl the way we just showed in these examples up here, if we actually go ahead and compute the curl, which is itself a new vector field, let's see how that works. So if you click on the second GIF, we should have this image here, and you can see it's the same original view of the curl that we had in when we studied Green's theorem, but now you can actually see that we've got vectors drawn here. So the vector we're going to learn in class corresponds to the axis of rotation. Now, because these are all 2D vector, these are all vectors living in the xy plane, they have no z-hat component, and the curl is always perpendicular to it, so the curl is always pointing in the positive z direction. Going forward, that won't be the case, but I still want you to think of the curl vector, and we'll discuss this more in class. I want you to think of the curl vector as the vector pointing in the direction of the axis of rotation. And you can see that happening here. This is rotating about this vector here, so it's rotating about the axis corresponding to this vector. Okay. Notice too that vectors have magnitude and direction, so this vector is pointing in the positive k-hat direction. That corresponds to that clockwise curl, and notice that its magnitude is fairly large, and that corresponds to that fast rotation, as opposed to this vector here, which is also pointing in the positive k-hat direction, corresponding to a clockwise rotation. But in this case, it has a small magnitude, and so it's a short vector. Here we have this vector rotating in the counterclockwise direction, so the corresponding vector could be thought of pointing in the negative k-hat direction. Now this all gets a little bit obscured once we're actually looking at vectors not just in the xy plane, but in all of R3. This is why this is a fairly difficult topic to try to illustrate. So we're just looking at this little slice here of this very simplistic vector field to get this intuition for our curl. So we'll discuss this more in class, but spend some time thinking about these two GIFs. This is what we studied before. This is actually what was going on. And now when we deal with a vector field in general, living in R3, and we go to compute the curl, we're going to get some vector field. And so then we'll have to learn how to interpret what that means. Okay, the last thing I want to say is sort of a mnemonic for remembering everything that we've done. So the curl, which we've written as del cross f, that's how we've written the curl. The word curl starts with a C, so does the cross product. Similarly, the word divergence, which we've written our divergence in our del notation as del dot f, that starts with the letter D, and so does the dot product. Folks, let's go ahead and, for my class here, we'll skip this. I'll pick this up in another video, or I'll pick this up in class. So we'll go ahead and skip this. Instead, what I'd like you to do, is go ahead and watch this video by Grant Sanderson, which is going to repeat some of the stuff that I've said before, but I think it does far better with the visualization than I can ever do. And then try number 14 on your own. So you try this. And then after that, I'd like you to go ahead and try this problem here, where I'm asking you to determine which of these operations make sense, which of them return vectors, and which of them return scalars. Okay? So give it a shot. I can look at this one already and say something seems fishy here, right? Because I take the curl of what type of object? I take the curl of a vector field, not the curl of a scalar valued function. So you'll see that. Go ahead and give it a shot. If you get stuck, there's a video solution to the above question. So you can take a look at that. So folks, your next step is, again, we're going to skip this conceptual question. I will answer that in class. But I'd like you to go ahead and then watch this video by Grant Sanderson, taking some notes, and then finish out these last two, questions 14 and 15. And then I will see you in class for our last couple of sections. Thanks.